The heading is Electrode Potential. Now, let's try to understand what is electrode potential. Think about a metal rod that is in a contact with the metal ion. Think about a metal rod that is in a contact with the metal ion. So let me think about a zinc rod that is in a contact with Zn plus ion. There is a beaker in which Zn strip that is dipped in a solution containing Zn ion. So in the solution there is a Zn ion and there is a metal strip. So when any metal strip that is kept in a contact with the metal ion, when any metal strip that is kept in a contact with the metal ion, there are two reactions going on. Which two reactions? One, metal loses electron and form metal ion. That is the one process going on. There is a one reaction going on when the metal is in contact with the metal ion. You can call it as a one reaction. And the other reaction in which Zn2 plus, let me write this in this way, Zn2 plus 2 electron that forms Zn. There is a other reaction going on. So, which two reactions, which two processes are going on? The metal goes into metal ion and the metal ion goes back into the metal. That two processes are going on. So both the process, one can be called as a forward process, one can be called as a backward process. And there will be an equilibrium between these two. There will be equilibrium established between these two processes. Which two process? Conversion of metal ion into the metal and metal convert back into the metal ion. So an equilibrium established between these two processes. So what will happen? The Zn atom in this case loses electron. It leaves electron on the metal rod. So electrons are on the metal rod. Now these electrons are actually lost by the Zn atom. The Zn atom which has gone into the solution. And in the solution, there is a positive ions. There is a positive Zn ions in the solution. So because of this, there is a electrons on the metal rod as metal has lost electron. And there is a positive ions in the solution. As the positive ions form in the solution after losing electron by the metal atom. These two oppositely charged ions, they attract each other and they form a double layer. They form a layer of this charge, the layer of this opposite charge. Because of this double layer of this charge, a potential is developed in the cell. That is called electrode potential. So that is called electrode potential because of these two opposite charge layer formed in the system. The potential of this half cell is called is electrode potential. So that is what the electrode potential. I have given an example of Zn strip where it is in contact with the Zn2 plus ion in the solution. So that is applicable when any metal strip you kept in the contact with a metal ion, right? That is one type of, this is called half cell. This is called half cell. Is this clear? So is anyone having any doubt in the electrode potential? First of all, what is electrode potential? Before I move further.
No, sir.
All right. So if you want to write the definition, I am repeating the definition once again. You can see the course book. In the course book, there is a diagram of this charge double layer. You can see the diagram in the course book. And there, above the diagram, they have given the definition of electrode potential. All right. So if you want, you can underline that definition. I am reading the last 3-4 sentences of this. The metal atom loses electron. This leaves an excess of electrons on the surface of the Zn. What I said. The solution around the metal now has excess Zn2 plus ion. What I said. Right. Some of these cations near the surface of zinc are attracted to its surface. The cations, they are attracted to its surface because on the surface of the metal rod, there is an electron, there is a negative charge. Okay. So an electric double layer is formed. This sentence you can underline. An electric double layer is formed. This buildup of charge causes an electrode potential. This buildup of charge of opposite ions that causes an electrode potential or voltage, you can say, between the metal and the metal ion in the solution. So that is called electrode potential between the metal and the metal ion in the solution. So is this clear to everybody? What is electrode potential?
Yes, sir.
Okay. And that electrode potential is called electrode potential of this half cell, because when we will form electrochemical cell is formed by joining such two half cells. When two half cells are joined, right, electrochemical cell is formed. So this is called one half cell. Now look at this reaction. Look at this reaction. It reaction has a two process. One process is a reduction. Reduction, Zn2 plus is going into Zn, and another is a oxidation process. Both the process are in equilibrium. Both are in equilibrium. Now let's consider about two cases. If the equilibrium lie towards the left side, let's say the equilibrium lie towards the left side. Equilibrium, a point of equilibrium lie towards the reactant side. So what I mean to say by this, a point of equilibrium lie towards reactant side. So what I meant to say by this,
Oxidation is
yeah,
happening. More oxidation is happening.
more oxidation is happening. Good, more oxidation is happening. So in this case, the extent of the backward reaction is more than the extent of the forward reaction. So you can write down case number 1. Let's say case number 1. An equilibrium point lies, equilibrium point is towards reactant side. Equilibrium point is towards reactant side. If the equilibrium point is towards the reactant side, as one of you said, more oxidation is happening. More oxidation is happening, right? And less reduction is happening. less reduction is happening. Okay, so in this case, the reduction potential of such metal ion system, it would be negative, and the oxidation potential of such metal ion system, that would be positive, right? So, like in case of the Zn, in case of the Zn, a point of equilibrium that lie towards reactant side. What that means? Zn has a more tendency to undergo oxidation, and Zn has a less tendency to undergo reduction. In case of Zn ion system, a point of equilibrium lie towards reactant side. That means Zn has a more tendency to undergo oxidation and less tendency to undergo reduction. So these electrode potentials that can be represented in a two-way. Make it very clear. This electrode potential that can be represented by two-way. Which two-way? One way is reduction potential. The one way to represent this electrode potential is a reduction potential, and the other way is a oxidation potential. By this two way, you can represent this electrode potential. Now, whenever the concentration of metal ion in the solution is 1 molar, consider the concentration of the metal ion is a 1 molar. So, if the concentration is 1 mole per decimeter cube of the metal ion, if the temperature is 298 Kelvin, you can note it down these values. When the temperature is 298 Kelvin, when the concentration of iron is 1 mole per decimeter cube, and when the pressure of any gas, in this half cell there is no gas, but there are other half cells in which gases are involved. So when the pressure of gas is 1 atmosphere, let's say if there is a gas in the half cell, and that pressure has to be 1 atmosphere. So if the pressure of gas is a 1 atmosphere, then that is called standard condition. And whenever we measure electrode potential in the standard condition, that is called standard electrode potential. So what is the standard electrode potential of any half cell? The standard electrode potential of any half cell is the electrode potential measured when the concentration of ions are 1 molar, temperature is 298 Kelvin, and the pressure of gas is 1 atm. Then that is called standard electrode potential. As I said, electrode potential that can be represented by two ways. We can talk about reduction potential, we can talk about oxidation potential. So let me consider in the standard condition, it is denoted as a standard reduction potential and the standard oxidation potential. If the half cell is in standard condition, the symbol is represented like this: standard reduction potential and standard oxidation potential. Now, if I write for the zinc, we can write in this way. In the symbol, we can write in this way. The standard reduction potential can be written like this: Zn2 plus 2 Zn. This symbol is called standard reduction potential of Zn. And the symbol for the standard oxidation potential of Zn is opposite to this. That is written E0 Zn, Zn2 plus. This symbol is called standard oxidation potential of Zn. Understood? Clear about this? In case of Zn, Zn's standard reduction potential is minus 0.76 volt. Zn standard reduction potential is minus 0.76 volt. What does it mean? As the standard reduction potential is negative, right? The Zn has a less tendency to undergo reduction. When it comes to reduction, the tendency of Zn is less. The oxidation potential, the standard oxidation potential of any half cell, it has exactly same value with the opposite sign. So Standard oxidation potential of Zn is 0.76 volt. So when I talk about oxidation, it is positive. When I talk about reduction potential, Zn is negative. Now in your book, mainly we will talk about only reduction potential, because you can talk about tendency to gain or tendency to lose. So throughout the chapter, mainly we will talk about reduction potential, standard reduction potential. So this is what the standard reduction potential, standard oxidation potential, as I said, throughout your book, throughout your course book, we will talk about standard reduction potential. So standard reduction potential of Zn is minus 0.76 volt. So what are the conclusion? The conclusion is Zn has a greater tendency to undergo oxidation. Zn has a less tendency to undergo reduction. Now, any metal which has a greater tendency to undergo oxidation, that is considered as a more reactive metal. Whenever we talk about reactivity of metal, usually we talk about its tendency to lose. When we arrange a metal in the reactivity series, because see, we used to say that Zn is more reactive than copper. We used to say that Zn is more reactive than copper. So in what sense we are talking? In what sense we are talking that Zn is more reactive than copper? We are talking in the tendency of losing electron. Whenever we are comparing the reactivity of metal, we are talking the tendency to undergo oxidation. We are talking that we are comparing the metal for the tendency to lose electron. The metal which has a greater tendency to oxidize, the metal which has a greater tendency to lose electron, that is considered as a more reactive metal. Because we know that when we arrange the metal, we used to speak like this, that Zn is more reactive than copper. So Zn can displace the copper ion. Zn can displace the copper ion. Okay. Now why the Zn can displace the copper ion? Because Zn has a greater tendency to undergo oxidation. As Zn has a greater tendency to undergo oxidation, the Zn, in presence of Zn, the copper ion will reduce to copper. Understood? So if I talk about reduction, the copper has a greater tendency to undergo reduction when compared to Zn. When I talk about tendency to gain electron, the copper has a greater tendency to gain electron compared to Zn. When I talk about tendency to lose electron, the Zn has a greater tendency to lose electron compared to the copper. Okay. But usually when we talk about reactivity of metal, we talk about the tendency to lose electron. Because usually we talk about which metal can displace which other metal ion. We talk in that sense. Understood? So that is called oxidation potential, standard oxidation potential, standard reduction potential. Now same system, if I do for the copper, let's say same the copper rod is kept in the copper ion, all right, and the concentration is kept, the concentration of ions are kept 1 molar. The copper ions are 1 molar here, and there is a copper strip, and it is also in the standard condition. Then again, both the processes are going on like in case of Zn. So let me write down that two process. The copper ion will gain electron and will go into the copper. That is one process which we call as a reduction. And think about the opposite process where the copper goes into copper ion, that is oxidation. Now, copper has a greater tendency to undergo reduction compared to oxidation. So when you check the reduction potential of copper, in case of the copper, its standard reduction potential is plus 0.34 volt. That is plus 0.34 volt. What does it mean? That means that copper, this point of equilibrium, that lie towards product side. In case of Zn, it lie towards reactant side. And in case of copper, it lie towards product side. Copper has a greater tendency to undergo reduction compared to the Zn. And the Zn has a greater tendency to undergo oxidation compared to the copper. Is this clear? Understood? So that is what the reduction potential of the copper, that is what electrode potential. And in this way, like we can talk about different metal ion system, and depending on the reactivity, whichever metal that is more reactive, in that case, the reduction potential you will find more negative. And if the metal is less reactive, the electrode potential you will find positive for that metal ion system. Reduction potential. So before I move further, do you have any query in this? First of all, do you have any query in the electrode potential topic? First, if you have any doubt, ask me.
No, sir.
So, are you clear about standard reduction potential?
Yes.
Okay. So we have discussed for which system. The system which I have drawn on the board is a which type of system?
Half.
Half cell.
That is a half cell. But which type of half cell?
Metal ion.
A half cell in which active metal, that is in a contact with the metal ion. Half cell in which active metal is in contact with the metal ion. Understood? So, are you clear about the half cell I have drawn on the board?
Yes, sir.
Yes.
Yes. What is electrode potential? What do you mean by electrode potential?
Tendency to lose or gain electrons.
Okay. The tendency to lose or gain electron, that is called electrode potential. Okay. How? Because of what the electrode potential this developed in the cell. Why it is developed in the cell? What is the reason? Why this potential developed in the cell?
Because of the double layer charge.
Because of the double layer charge, right? And why the double layer charge formed? Because when any metal is in contact with the metal ion, the metal will lose electron, leaving that electron on the metal rod. That forms a negative charge layer on the metal rod. And after leaving electron, it forms positive ions in the solution. These positive ions, they get attracted by this negative charge layer, and this double charge layer form. And that is because of that electrode potential or the voltage is formed. Is this clear? Understood? Now, what is the standard condition of any half cell? What is the standard condition of any half cell?
298 Kelvin.
When the concentration of ions are kept 1 mole per decimeter cube, when the temperature is at 298 Kelvin, and the pressure of any gas, if any gas we have passed, the pressure of gas should be 180 m. That is called the standard condition of any half cell. And when we measure electrode potential in a standard condition, what that is called?
Standard electrode
That
potential.
is called standard electrode potential. Standard electrode potential that can be represented in a two-way. Which two-way?
Oxidation and reduction.
Standard reduction potential and standard oxidation potential. For any system, the numerical value for both, that is same, only sign differ, and that is understood. If the tendency of losing is more, obviously in the same proportion the tendency of gaining is less. So the numerical value remains same of standard reduction potential and oxidation potential, but only sign is different. Understood? Clear about this? In your course book, as I said, they have represented electrode potential by which way? Most of the time,
Reduction.
they have used standard reduction potential throughout your course book, because every time we are not going to represent both the tendency. So throughout your course book, they have used standard reduction potential of half cells. Understood? Now, my next question, if any half cell has reduction potential, standard reduction potential, negative, what does it mean?
Metal.
If the standard reduction potential is a negative, what does it mean?
It has more tendency to lose electron.
More tendency to lose electron, in case of metal, we can use a term that metal is more reactive. We can use a term that metal is more reactive, right? And if it has tendency, it has a more tendency to lose electron. Can I say it can act as a better reducing agent? Right? So note it down. Note it down. This is very important. If the standard reduction potential is negative, if the standard reduction potential is negative, the metal is more reactive. Metal is more reactive and is better reducing agent or good reducing agent, and it can act as a better reducing agent or good reducing agent. And if the standard reduction potential is positive, like in case of the copper, if the standard reduction potential is positive, like we have seen in the case of the copper, the metal is less reactive. The metal is less reactive. It has a greater tendency to gain electron. It has a greater tendency to gain electron. So it is a poor reducing agent. It is a poor reducing agent and the better oxidizing agent. It is a poor reducing agent and better oxidizing agent. Written?
Yes, sir.
Okay. Can anyone repeat what I said? These two things. Anyone would like to repeat what I said? This the first. What I said the second. How to conclude whether it is a poor reducing agent or better reducing agent. Okay.
The lower the electrode potential, the more reactive the metal and better reducing agent it is.
Good. The lower the reduction potential, more reactive metal, better reducing agent, poor oxidizing agent, and poor oxidizing agent. Right? That was point.
Yes.
That was point number one. What was point number two?
Mm. High potential, better oxidizing agent, poor reducing agent.
Good reducing agent. In which case, if the reduction potential is
High, then good oxidizing agent.
if the reduction potential is positive,
Mm.
that is better oxidizing agent
Yes.
and poor reducing agent.
Mm.
And poor reducing agent, and the metal is less reactive. The metal can be concluded as a less reactive. Is this clear to everybody? What is called electrode potential? Should I remove this from the board?
Yes,
What, sir?
sir.
Now, you put the heading non-metal ion system. Non-metal ion half cell. Earlier what I discussed, that was metal ion system. Now this is non-metal and non-metal ion. Let me give you example of such one half cell. See the construction I am drawing on the board. A solution containing H plus ion. a solution containing H plus ion. Electrode in this system is usually not active electrode. Inert electrode are used. So electrode is platinum. Electrode is platinum, and a gas, hydrogen gas, is passed over this platinum electrode. The pressure of hydrogen gas, I'm talking about standard condition, it is kept 180 m, or you can say 101 kilopascal. The concentration of H plus ion is kept 1 mole per decimeter cube, and the temperature is kept 298 Kelvin in the standard condition. This half cell system is called non-metal in a contact with the non-metal ion. Non-metal in a contact with the non-metal ion. Now, can you tell me what would be reduction reaction in this case? What would be the reduction reaction?
H plus to H gas, hydrogen gas.
H plus plus E to H2 gas. To balance, we can write 2H plus 2 electron and the H2. That is a one process that can be called as a reduction process. And what is the oxidation process?
H to H plus.
Opposite. The opposite reaction is called oxidation process. That is oxidation process. Alright? And remember, this half cell which I have drawn on the board, that is used as a reference electrode. So you can put the heading, it is a reference electrode.
Meaning, sir?
Reference electrode, see, you cannot measure electrode potential of any half cell. Practically, it is not possible to measure electrode potential of any half cell because the flow of electron is within a system, within a cell. Electrons are not flowing outside. So you cannot measure electrode potential of any half cell. So how the electrode potential of any half cells are measured experimentally? To measure it, you have to take one reference. You have to take one reference electrode. They are joined with the reference electrode so that electrons can move from one half cell to another half cell externally. There will be external, an electrochemical cell is formed by joining with the reference electrode. So the electron flow from one half cell to another half cell, and with reference to that half cell, the half electrode potential of all the half cells are determined. Are you understanding what is the reference electrode?
Yes, yes. Like carbon for mole.
Yes?
Like carbon is for mole.
Yes, yes. For the atomic masses, to measure atomic masses, they have chosen one standard of the 1/12 of carbon 12 that they have taken as a reference. And you can understand the reason why they need a reference in this case. Because think about that metal-metal ion system. In the metal-metal ion system, you tell me how you will measure this electrode potential. Is it possible to measure this electrode potential? Because electrons are not flowing externally. I cannot put any device. I cannot measure the voltage. Whatever is happening, the exchange of electron is happening inside in the system, right? So for that, I need to join the system with some other system, which can I take as a reference, all right? And I can take that system as a reference, so the electron, they move from one system to another system, and then I can measure the electrode potential relative to this reference, relative to this standard. Are you getting what is the reference electrode? So this, which I have drawn on the board, that is used as a reference electrode. That is called standard hydrogen electrode. What I have drawn on the board, that is called standard hydrogen electrode. And that is used as a reference electrode to measure standard reduction potential of half cells. Is this clear? Are you clear about non-metal metal ion system, everybody?
Yes, sir. Sir, the meeting is going to end.
Yes, it is going to end. So I will keep the topic up to here. You write down one question before it end. Draw construction of chlorine gas and the chloride ion. Chlorine gas and the chloride ion half cell and electrode is platinum. Electrode is platinum. Draw construction of chlorine gas and the chloride ion. Platinum electrode. Write equilibrium of this metal ion system. Write equilibrium reaction of this metal ion system. So are you clear with the question? What I did for hydrogen, the similar thing you have to do for the chlorine. The gas they have passed is a chlorine here. The ion in the solution is a chloride ion with the